How do I make this full screen? Where?
There's a plus and a minus. Go down.
That one?
Yeah, that one. First.
No, that just makes it bigger. I don't know where the full screen.
Yeah, I think it's fine.
I think it's fine, yeah.
Okay.
Can I start?
Yeah.
Okay. I'll leave the door open because it's so stuffy in here. So the last lecture we were introducing this concept of order out of chaos or order from noise. That means if you put random variation into some kind of a system, if that system has a certain preference, that means if it likes to settle in a particular kind of order, by shaking it more, that means by injecting more random variation, we will make it self-organize faster. And here is another little experiment that you can do yourself. You take a paper clip, you open it a little bit so that one paper clip can slide into another paper clip. You put a bunch of these paper clips in a box, and then you shake the box violently, and you will see that you will get some kind of a branching chain of different paper clips that are attached to each other. So what is the principle here? We're speaking about variation shaking the box. Variation is random, it doesn't have any preferences, but the paper clips are such that one paper clip can easily slide into another one, but by shaking it, it's unlikely to come out again. So the more you shake, the more you get one paper clip slipping into another, but they are unlikely to come out again, so you will just get more chains, more connected paper clips. So it's a very general principle of self-organization. Random variation, if there is a selective preference, will lead to faster evolution, to faster self-organization, to faster reaching of a state, what we call an attractor state, a state where you can enter but you can't get out. So this gives you a very general, I would say, philosophical principle, which is that to evolve complex structures, you don't need more than random variation, random, or a term that I prefer, blind variation. Random in principle has a kind of a technical meaning in the sense that random means that every possible variation has the same probability as any other possible variation. In most cases, it will not be exactly that all the probabilities are the same. But what we need to know is the variation is blind in the sense that it does not know which of the results will undergo selection. So we have these two components, variation and selection. Selection means there is a preference for certain configurations over others. We say that variation is blind if the variation does not know which are these configurations for which there is a preference. So in the case of the paper clips, the implicit is for the paper clips to be connected together, but the shaking of the box does not know that. When you shake the box, the paper clips are just moving randomly. They have no idea where they should slip into. But if they happen to slip into another paper clip, they will tend to stay slipped into that paper clip. So that is now the very general principle. Evolution can build order on the condition that A, there is variation, B, there is selective preference, and the variation can be blind. It doesn't need to know anything. And that is counterintuitive because we saw in the very beginning of the course, we saw the watchmaker argument. The watchmaker argument is you see some complex ordered system there, you say that can't have happened just randomly. There must have been an intelligent designer who thought about how to put all the elements together in the right order. In the case of the paper clips, of course, it's a much simpler system than this watch that was used in the parable of the watchmaker. But yes, it does self-organize to random shaking, that means to variation that does not have any idea of what is the right configuration. Now, blindness, it doesn't imply that all variation is blind. Some variation may have a preference for certain directions, which turn out to be better directions. But the principle is that even if the variation was purely blind, even if the variation didn't have any foreknowledge of what are the solutions, the good things that are preferred, even then evolution would work. So that is a very fundamental principle. The moment there is some kind of a selective preference, blind variation is enough to tend to get more and more of this selective preference. Now, what is a selective preference? This is a selective preference for a fit state. We will in it like those paper clips where you easily get into, but once you're into, it's difficult to get out. So another way of understanding that is evolution is a problem-solving process. The problem that evolution tries to solve is build the fittest possible system. Evolution doesn't know which is the fittest possible system. What evolution does is it blindly tries out all these different possibilities, and the moment that it finds one that's fitter, when it keeps it, and then it adds some more variation, it makes it even fitter, and it makes it even fitter. That's all. You don't need any foreknowledge, you don't need any intelligence, any design. Now, problem solving in people, there is intelligence. If I solve a problem, I typically have some idea of what might work and what might not work. That's what we call a heuristic. Typically, you have learned to apply certain methods, and if you apply these methods, then probably or maybe you will get to a solution. There's nothing that says that in evolution you can't get these kind of shortcuts. Sooner or later, living organisms like plants and animals, they will develop some kind of a knowledge, so they will no longer be blind. They will be able to search in a more systematic way. But the important philosophical principle is it does not need to start with knowledge. Starting with complete ignorance is enough. There was a question there.
Is the evolution infinite?
Infinite.
Yeah, does it keep on going?
Yes. There is no reason whatsoever why it would stop, because the number of elements in the universe is so large that if you look at all the possible combinations that you could make of all these possible elements, it is an unending thing. So evolution will continue making new combinations of existing elements, and some of these new combinations, as we will see, form a new system. And that new system then becomes a component that then you can use to combine with other systems. So you build the one on top of the other, and there is no end to it. But now, that's a very simple, very broad view. We need to go into a little bit more depth, because we know there are these people who do not believe in evolution, who want somehow to prove that you need an intelligent designer. So there is this intelligent design camp that tries to find arguments to show that evolution based on blind variation cannot work. Now, not all their arguments are stupid. We will now discuss one very good argument, and then we will also find the counter argument. How did evolution solve that problem? And that example is often shown by Hoyle's Boeing. Can you show the next slide?
Sure.
So Fred Hoyle was an astrophysicist. I wouldn't say that he was an intelligent design theorist, but he was somebody who was very skeptical about the fact that evolution could have created life on Earth. He had some little bit strange theory called panspermia, that life would have originated somewhere else in the universe and somehow gotten onto the Earth. And to strengthen his reasoning, he gave this example of the Boeing. That is, imagine that you have a junkyard in which there are all kind of possible pieces of metal and plastic. You have a tornado going through the junkyard. The tornado is random variation. It just mixes up all these pieces, just like we did with the paper clips. It just randomly shakes all these pieces in the junkyard. What is the probability that this random shaking of components would lead to the creation of an airplane, a Boeing 747 in his example, that would ready to fly away? I think it's intuitively clear that that is never going to happen. So let's try to explain why the paper clips do form these chains, relatively simple things, but something as complicated as the Boeing would never happen through random variation. So we need to go into more depth. What is it that evolution needs to build up? And we'll start as a kind of a thought experiment. We assume that there is a very simple organism, the simplest possible bacterium, and we assume that the bacterium is defined by its DNA. That means a sequence of strings. In DNA, you can say that the codons, that means the little bits of DNA that code for one amino acid, they are kind of like the words in the language. So it's the language with which DNA codes for life. You have the individual words or the individual letters, and now you need to build a DNA string of the right shape in order to create something that is good enough to survive. So the example I take is, let's assume that this string has 1,000 words. 1,000 words, so it's like as if I have one long text that is describing how to build this very simple organism, and I assume that the text consists of 1,000 words. Now I know the words that DNA uses correspond to amino acids, and there are 20 amino acids that life uses to build proteins. With the proteins, it builds cells. With the cells, you have life. So what I need is a text of 1,000 words. How many possibilities do I have for the text? For the first word, I have 20 possibilities. For the second word, I have 20 possibilities. For the third word, I have 20 possibilities. For the fourth word, I have 20 possibilities. In other words, I have to multiply 20 with itself 1,000 times. 20 to the power 1,000. Now, if you calculate it, that's roughly 10 to the power 1,301, which means it's a 1 followed by 1,301 zeros. I wouldn't know how to call such a number. That's not a trillion, that's not a quadrillion, that's not a gazillion. It's so big. There aren't enough atoms in the universe to express a number like that. What have we tried to do? We have tried to specify a very simple organism that has only a string with 1,000 DNA codons. All the bacteria we know are much more complicated than that. Yes?
So a codon is not an individual letter, but the actual word of the amino acid, as to say how the amino acid behaves then. Or
A codon is, well, I don't want to go into the technicalities, but you have 4 bases, which corresponds to 4 letters. Each combination of 3 letters corresponds to 1 word. That's a simple way to say it. So you have the letters, which are the bases. You have the words, which are the triplets of 3 bases. You have the sentences, which are the genes coding for one protein, and then you have stop signs in between the genes, so you have a text. Just say we are writing a text, we can choose out of 20 words, and we need to put each of these words in together in one long text that is 1,000 words long. So as I said, the number of possibilities is so absolutely astronomical that no way ever you would find it. To give you an estimate, so let's assume that you start the process of variation at the very beginning of the universe more than 10 billion years ago, and that the variation produces one new attempt every second. Then you get 10 to the 17 possibilities that variation can explore. You need to have this. This compared to this is nothing. It's completely negligible. So that was assumption that you have one variation per second. For you say, well, we can do it much faster. Let's do it 1,000 variations a second. Then you get 1020. Let's do it 1,000,000 variations to the second. Then you get 10 to the 23. You see, you will never get there. So that is the argument of Hoyle, but put in form. So yes, he is right that to generate even the simplest possible organism by purely random variation, the probability that you would get there is so small it will never happen. Now the question is, how did evolution do it? For that, I will introduce a very important principle, which I call the stepping stone principle. Can you switch to the next? Oh. Is there maybe a bad contact zone?
Somehow, yeah. I don't know where.
So let's look at a simpler example, one of these old-fashioned banks where you still have a safe that you can try to open, and let's assume that that safe has 6 numbers, and the numbers go from 0 to 9. So for each of the 6 numbers, there are 10 possibilities. So the first number, 10 for the second, 10 for the third. That is 1,000,000. Can you go to the next one?
Mm-hmm.
So here there are 5. Imagine something like a byte block, but with 6 numbers. Yeah, a byte block with 6 numbers. You will never find the right possibility. Nobody is going to try 1,000,000 different combinations in order to break open a byte block. Now, these safe crackers, which you sometimes will see in old movies, they had a trick to do that. And what they usually did is they had a stethoscope, and the stethoscope, they would put it next to each of those dials, and then they would turn the dial very carefully, and they would listen. And they would, at a certain moment, hear a sound that's different from the sound of the other numbers. And why is that? Well, if the safe has been opened many times, it means that many times people had to switch it to the right number. So that means that the right number is slightly worn out. So if you turn the dial to this number, you will hear a different noise than if you take one of the unused numbers. So let's say that the safe cracker turns each of the dials to all of the 10 numbers until he hears a click. That means that for the first dial, he has to try at most 10 times until he hears the click. For the second dial, he has to wait at most 10 times until he hears the click. And you get the same, but now you get a sum. 10 plus 10 plus 10 plus 10 plus 10 plus 10, to say 6 times 10. At most, 60 attempts will get you to the right solution. You will have the 6 dials in the right position. The safe will open, and you can burgle the bank and take out all the millions. So, what is the principle here? Here you have to try out 1,000,000,000 possibilities. Here you get it after maximum 60 possibilities. The principle is that you hear the click, and what does the click do? The click tells you you're on the right way. You're step one towards solving the problem. That means the moment you hear the click on one of the dials, you know you don't no longer need to touch the dial. You can leave it in place. You go to the second dial until you hear the click. The moment you hear the click, you know the second dial is in the right place. I can leave it. So what the click does, it tells you you have part of the solution. Go on to the next part. And that makes the whole thing, of course, much, much easier. So let's assume that we could use a click here. And instead of 20 times 20 times 20 times 20, we would have to do 20 plus 20 plus 20. It means we would have to do 20 times 1,000, 20,000 attempts. Now, 20,000 attempts for evolution, that's trivial. Here we were speaking about 10 to the 23rd attempts. 20,000, that's almost nothing. Of course, it's not that simple. It's not as if evolution will get the equivalent of a click each time it gets one amino acid correctly. But what is happening is that evolution does not immediately make the whole complex systems. It makes it step by step. So that's why I call it the stepping stone principle. What you need is intermediate steps. You have a complex problem. You are here. You need to get there. How do you get there? It's too far. You do it step by step. Can you go to the next slide? So it's the same principle as the river is much too wide to cross on its own. But if there are stepping stones that are not too far apart from each other, you just go from step to step. Now, here, of course, you know you need to go there. Evolution does not know. Evolution is blind. So evolution will go here and here and here, but occasionally it will stop on the right stone. And once it's on the right stone, it will not go back. It will again try all different possibilities until it gets to the right stone, etc. Yeah.
So then a stone represents a certain amount of fitness.
Yeah.
Because otherwise it would once again be Newtonian and one answer.
Yeah, what the stepping stone principle says is there are intermediate stages that are fit enough to survive. They don't need to be very fit. They don't need to be very sophisticated. It's enough that they're stable enough that from that stepping stone, now you can try out many different possibilities. So imagine that you would have to cross that river in the dark and you can't see the stones. Maybe you will try out with your foot until you feel something hard and then you do the step. That's how evolution will do it. Can you change? So evolution, let's say, starts here. You want it to get to the other side. It goes from step to step, and as long as the steps are not too far apart, it doesn't take too much trials and errors, not too much variation to find the next step. So let's apply this to a more concrete example of evolution. One of the criticisms that were raised against the theory of Darwin when he first proposed variation and selection as an explanation of how organisms could have evolved, people were saying that can't work. Imagine something like the eye. We know the human eye is a quite complex thing. You need to have a lot of different organs and things in place to have any working eye. So now if you would apply the stepping stone principle in a naive way, you could say, okay, we'll start with not with a full eye, but we'll start with 1/10 of an eye and then go to 2/10 of an eye and then go to 3/10 of an eye. And then people would say, yeah, but what is 1/10 of an eye? It doesn't make sense, it doesn't work. But of course, evolution doesn't work with 1/10 of an eye. Evolution works with something that is not yet an eye, but that is useful enough to get there. So how could we evolve that complex eye in steps? First step, you need to have a creature, let's say some kind of a worm, and part of the skin of that worm becomes sensitive to light. With sensitive skin, you can't see anything, but you can see the difference between dark and light. And for a worm, that can be useful because, for example, if the worm comes out of the soil in the day, it's likely to be eaten by a bird. If it does that during the night, the bird won't see it and it will survive. So having a little bit of light-sensitive skin is a useful thing. So let's make a drawing. So imagine I have my worm-like creature, and the worm develops something, a light-sensitive patch. Okay, it can distinguish light from dark, but that's all. But now imagine that light-sensitive patch gets this shape. That means if the sunlight is like that, that part will get more light. If the sunlight is like that, that part will get more light. That's useful for the worm because now it knows if I go into that direction, I go towards the sun. If I go in that direction, I go away from the sun. That already becomes more useful, but let's make it even more useful. Let's assume that the shape becomes something like this. There is still the light-sensitive skin. But now it can distinguish many more directions. Depending on how the light comes, these different light-sensitive parts will get different amounts of light. This is already starting to look like what's called the camera obscura, kind of a very simple way of projecting images. But now, of course, that kind of construction, it's like having a hollow in your skin, all kind of dirt can get into that. So it would be better if here you have a little bit of transparent skin that protects that light-sensitive layer. Now, if you have a little bit of light-sensitive skin, well, then it could be that light-sensitive skin becomes, that kind of transparent skin, that transparent skin becomes a little bit thicker in the middle and on the sides. Now you already see what we are getting. We're getting something like a lens. Now, how can we make that even more sophisticated, that lens? Well, if on the sides of the lens there would be muscles that can pull on the lens, they can make it flatter and they can make it less flat, then the lens can focus. Depending on whether the light comes from far or from close, it can focus. We're getting something that's looking very much like this eye. What more mutations or variations could we invent? Well, we assumed that there was light-sensitive skin, but we didn't say to what color the skin is sensitive. Maybe if there would be some mutations in these light-sensitive cells, so that some are more sensitive to red light, and some more to green light, and some more to blue light, well, then we would have actually an eye that can see colors, that can focus far and near, that can have very clear vision. Basically, we have evolved an equivalent of the human eye in 6 steps, and each of these steps itself is pretty easy for evolution to do. So that's a scenario I kind of made up. How do we know that that's realistic? Well, we can look in nature and we see that there are different creatures that have different types of eyes. Can you switch? And mollusks, you can have the limpet, which is a kind of a creature that just sits a little bit like a muscle that just sits on top of a rock. It just has this light sensitive part, and then you have others. Then you have others where indeed you have already that kind of a hollow, and then you have something like the camera obscura, and then you have something like the lens. And the more complicated the creature, the more sophisticated the eye. Something like the octopus has evolved an eye that is very similar to our eyes. And the funny thing is that people are not at all related to octopuses. So the fact that this octopus developed an eye that's pretty similar to the human eye, it just means that these different steps are pretty obvious for evolution to take. And yes, why wouldn't they be obvious the way I explained it? It doesn't mean that it's the only solution, because we also know that there are insects who have eyes that consist out of lots of little independent parts. So the insects have evolved a different solution, but obviously it's not difficult for evolution to go through that whole stage and to build something increasingly complex in small steps. So we have a kind of counter-argument against Boyle and the intelligence design camp. So instead of saying the tornado will immediately construct a complete Boeing, we are saying, well, maybe the tornado will push some things together, and these things that are pushed together may get with some other things together. And of course, we will not get the Boeing, because why would tornado ever build a Boeing? But we may see some self-organization in the junkyard. And if we wait for millions of years to life, we will see pretty complicated things emerging. But so the intelligent design camp has not yet given up. So they use their last, and you might say their best argument, an argument that was proposed by a biochemist called Michael Behe. He introduced a very interesting concept, the concept of irreducible complexity. Irreducible complexity means you have a system that's complex. That means there are many different components that are working together, like maybe the components of an eye, but such that you need all the components at once for anything to function. In the case of the eye, that's not the case. The eye is reducibly complex. We can subdivide the eye in these different parts, and each of these parts is useful instead. So what Behe says, well, if we look in life, we will find certain cases of what he calls irreducibly complex things. Things where all the components need to be in place. You can't build it up step by step. And a simple example of an irreducibly complex object would be a table. A table has at least 3 legs, and the tabletop, you need all 4 components. You need at least 3 legs and a tabletop to have a table. A table with 2 legs will fall. A table without a tabletop, you can't put anything on it. You need at least 3 legs and a tabletop to make a table. So Behe gave some examples in his book of what he claimed to be irreducibly complex systems in the living world as a kind of argument to say, yes, we do need some intelligent design. So it's always the same motivation. These are people who want to imply that God had some kind of a role in the creation of life on earth. So the creationist view is God just made them stay the way they are. The more sophisticated intelligence design view is, well, there was evolution, we can't really deny that, but the evolution could never have worked only with blind variation. There must have been some kind of a guidance, some kind of an intelligent design that put all these components in the right way together, because these components could not have been added one by one, as the stepping stone principle would say. So now we need to answer that question. So yes, there probably are a number of things in life where you see that a number of components are working together in such a way that if you would take out one component, then the others wouldn't function anymore. Now, let's take a very simple example. Birds fly using feathers. They have special feathers in their wings, feathers that are such that if the bird is like that, the air can't get through, but if the bird pulls up its wing, then the air can pass through the feathers. So that's how birds fly, they just do that. If they push down, they're kind of pushing themselves up in the air. If they push up, the air passes through their wings. So to fly, birds need feathers and they need wings. You need both parts. So how could each of these parts have evolved on its own? Well, actually, it's not that difficult. Can you go to the next one? So what we know is that birds are descendants of dinosaurs, and the latest research gives more and more indication that actually the dinosaurs already had feathers, even long before they became birds, even long before they could fly. And why would they have feathers? To keep warm. Now it turns out that dinosaurs most likely were warm-blooded, just like birds, which are their direct descendants, and mammals. And mammals have just hairs. It actually becomes more efficient for warmth insulation if instead of single hairs you have something more fluffy. But these kind of more fluffy things, they can also get that kind of a shape. And eventually, you get to that shape, and that is the right shape for the feather that a wing that a bird uses in its wings. So this is something that is called exaptation. Adaptation means you evolve a particular feature that is adapted to your environment. For example, if you are in a cold environment, you can adapt by growing a thicker fur, like a mammoth had a very thick fur. An African elephant doesn't have any fur. The African elephant is adapted to the warm climate of Africa. The mammoth was adapted to the cold climate of Siberia. Exaptation is you evolve something that is adapted for a particular function, and then you start using it for a different function. So this feather evolved, was adapted to keep the bird warm, or the dinosaur, and then it was exapted, that means it changed its function, and it started to be used to help the bird to fly. So exaptation is something, if you look in evolution, you find many examples of that, of an organ or a system that evolved to a particular function, it was adapted for that particular function, and then it got a very different function, and the original function, actually nobody cares about it anymore. There's another example, modern fish, by which I mean the fish that have a bony structure, that means excluding the sharks and the rays. Modern fish have a swim bladder. A swim bladder is a kind of a little sac inside a body that is filled with air, and the swim bladder is used for the fish to determine where in the water it should float, deeper or higher up. If the air is compressed, the fish becomes heavier relative to its volume, so it sinks. If the swim bladder is expanded, the fish becomes lighter and it goes up. So thanks to the swim bladder, modern fish can keep at the right position in the water. Sharks can't do that. Sharks have to swim, otherwise they sink to the bottom. So sharks cannot regulate their vertical position in the water without moving. So that means they always have to spend energy. They have to continue swimming because otherwise they will just sink to the bottom. So now, where does the swim bladder come from? Well, it has been reconstructed that this comes from primitive lungfish. And lungfish evolved in a very different milieu than where those modern fish, most of them live. Lungfish lived in small ponds on land, so not in the sea, kind of muddy ponds, where it could get quite hot and where there was not enough oxygen in the water. So what these lungfish did, they went to the surface, and like you sometimes see a goldfish do, they would swallow some air because their gills, to which they extract oxygen from the water, couldn't get enough oxygen. So these lungfish would simply swallow a little bit of air. So in order to keep that air, they developed a kind of a sac, kind of a primitive lung, out of which they could extract the oxygen. But then when these fish got back into rivers and seas where there was enough oxygen, they no longer needed to go up to the surface to swallow some air. They just had that air inbuilt in their body, and they use it as a swim bladder. So the swim bladder is an example of exaptation. It starts as a function as a primitive lung. It ends up as a swim bladder, and the lung function just gets lost. So now, how does it explain the paradox of Bay? Huh? Yes?
Are these fish then the ancestors of, for example, dolphins and stuff?
No. Dolphins are mammals. So, no, the lungfish. There is a famous example of a coelacanth. I don't know whether you've ever heard. So coelacanths were primitive lungfish that were found in fossils that were like, I don't remember, 200 million years old. And people thought that they had died out a very long time ago because they looked very strange as coelacanths. And then I don't remember when, somewhere in the 1940s, some fisherman that was dragging very deep in the ocean got a big coelacanth out that looked almost exactly the same like those fossils of 200 million years ago. And that coelacanth looks a little bit like the kind of thing that you might imagine that was kind of crawling in the mud. Because the coelacanths, they don't have the fins like the normal fish. They have fins that are a little bit kind of like the beginning of a leg, so they can push themselves up. But these coelacanths obviously evolved on land in muddy pools, but then they got back into the ocean, and of course, whatever adaptations they had for living in muddy water, they lost. But you can still recognize anatomically that these things are still there.
There's also mud skippers still living there.
The mud skippers are still living like that, yeah. I have once been trying to catch those. I was in Bali in a laguna. That means a kind of a muddy surface that gets covered with sea on high tide, and it is just mud in low tide. I wanted to catch some of these fish from my aquarium, but they are so fast, they jump like that. You can't catch them. So, how does exaptation solve the paradox of Behe? So imagine you find some creature that has certain collection of organs that work together as a system, and the system can only work if all of the elements are there. Well, what probably happened is that these elements were added one by one via the stepping stone principles. But each time the stepping stone was to adapt to one particular problem, and then something else happened, and then maybe that organ was used for something slightly different, and then something else was added, and then these organs started collaborating with other organs, And while doing that, they lost their original function, so that now all of these organs have only this specialized function within this complex system. And then somebody like Beyer can say, yes, but that system is irreducible. I cannot take out any components because all of the components are necessary. But what probably happened was that the components were added one by one, each component giving a little bit of an advantage, and then these components were exacted for different functions. The original function was lost. So people will say, yeah, that component is that it can only do this one thing, and in order to do this one thing, it needs to have all these other components. Yes, maybe that's the case now. That probably was not the case in the history of evolution. And so all the people who have been looking, the biologists, into the examples of Bayer, they have found plausible scenarios in the style of the scenario I gave for the eye, where you could indeed imagine a number of intermediate steps that would let all these components evolve so as to, in the end, make something that's irreducibly complex. But yeah, it could have evolved step by step. Sure. So the stepping stone principle, the first picture I showed you, it was pretty obvious how you get over the river. But pretty obvious, that's the way you would reason if you know where you want to go. If you are here and you want to go there, yeah, you will say, that's the way. And then you say, but there are no stepping stones in that direction. Impossible for evolution to get from here to there. But that's not the way that evolution reasons. Evolution is exploring an immensely large state space of all possible combinations of features that is so multidimensional we could never even describe it mathematically. And whenever evolution finds some combination of features that's good enough to survive, it will stay there, and then it will find some other combination of features that's good enough to survive, and then another one, and then another one. And it can make any detour. Evolution is blind. Evolution is not trying to get from there to there, but it may end up there via this detour. Because evolution doesn't know what is at a detour. We, let's say, as designers, if we, suppose that you're an engineer and you want to build a system, you have a kind of a plan, you have a kind of an idea of where you want to get. For example, you're a carpenter, you want to make a table, you know that you need to take 3 or 4 legs and put them in a particular way. It's obvious what are the steps. For evolution, nothing is obvious. For evolution, just try out anything that works. If it works, continue trying to make it even better, and you can take any kind of a detour. That means that you can start with something that you use as a lung, and then in the end you decide that you don't need lungs anymore because you're living in the deep sea. But what you had as a lung turns out to be very useful to keep your vertical position in the water. So that is how you can explain these examples of irreducible complexity. There are still stepping stones, but it's just that the stepping stones are not necessarily in the simplest or in the most obvious way. They can take all kind of detours, going in directions which afterwards turns out that you don't need it anymore, coming back close to where they started. But in the meantime, having developed all these different functions and all these different organs. Okay, so we'll have a 10-minute break here.
The cable. You can plug it in here.
How come they don't always switch immediately?
What doesn't switch immediately?
The slide.